All right, so we are now ready for scalarization, both linear scalarization and nonlinear scalarization. So characterizing optimal elements of vector optimization by scalarization by the replacement of vector optimization with a parameter-dependent optimization. So, for example, methods such as weighted or epsilon constraint, all of them are a special case of Pascoaletti-Serafini. And so we have a vector optimization, we can be converted into a scalar optimization. And this is the only framework, the theory of Gabriel Eichfelder, then you can systematically do that. Otherwise, methods such as goal programming or these methods, especially polynomial goal programming, they don't work for actual problems, and it is a blind way of doing scalarization. So a convex cone is you can the intersection of all of these set valued maps is a convex cone, and we call it D hat. And you can also take the union of all of them and the dual cone. And it is interesting that if D of y, if D set valued map vary very slightly, then even linear functional are enough to separate these convex sets. So you see how linear functionals are enough for convex sets. But for a non-convex set, or when D of y vary too much, then you need to use nonlinear functionals. In this lecture, I only introduce one of those nonlinear functional, one or two of them. In the next lectures, I also talk about different nonlinear functionals as well. So if you have two sets, such as S and T, that both of them are convex, and you can find a linear functional that separate them. For example, say from here, all of them, L of S is less than alpha. And from here, all of them, because it's on the right side, we can say that L of T is greater than alpha. So you can separate them because these sets are convex. These sets are convex, and you can use linear functionals and minimize a linear functional to find the efficient frontier. So if so a linear functional L exists that we can separate them, and the proof is very simple, and we use theorem 441. We use theorem 441. We use this theorem that if you have two different convex sets, you can separate it by functional. Then we use this theorem to say that, okay, if A is convex, then y bar is a weakly non-dominated element of A, then a linear functional exists, which is if you minimize it, you can find that Ly bar is lower than L of y. So the functional evaluated at y bar, which is a weakly non-dominated element, is less than that functional any other place. And you will see that this holds even for non-linear functionals as well. For example, here we have a set-valued map. We are doing scalarization, linear scalarization here, and our objective, for example, A is inside that objective space that you want to minimize looks like this. If you, for example, put L like this, then it's enough to say that to find some non-dominated elements. So nonlinear scalarization, when d of y varies a lot, or you have non-convex sets, it plays an important role. And this is the distance function, but delta as a y is sign distance function or this function, and has many properties as well, such as if it is less than 0, then you say that y is inside S. You are on the boundary if it is equal to 0. And characterization of non-dominated elements can be done with this non-functional, with this nonlinear functional as well, because for example, if you want to see if y bar minus y is inside that set valued map, it is enough to say that that functional should be negative or equal to 0. And so you're trying to characterize all non-dominated elements with just a simple functional, nonlinear functional. And this is a very important theorem, and we will use it in lecture 7, which is the last lecture about numerical algorithm. And you see if y bar is a non-dominated element, then it should be the smallest. The value of your functional becomes the smallest and equal to 0. For example, in the case of Pascoaletti-Serafini, you just put t is equal to 0. For y bar, which is a non-dominated element, t is equal to 0. And then you can say that y bar is a non-dominated element. And it is a unique minimal, so they both coincide. It is both a minimal element as well as a non-dominated element. So using that functional, so using that functional, we can completely characterize minimal elements. And also, not only we can characterize non-dominated elements, but also we can characterize minimal elements as well. So here, tau is just delta is defined like this. So it's a nonlinear functional, and again, the minimum of this functional corresponds to the unique minimal solution of this minimization. And so we have found a functional that if we minimize that, we can find at which point it is a minimal element, and the minimum is the minimal element of that. So a particularly important translative functional is, I think this one is also called Gershwitz functional in Temer book, and but our approach, which is based on BP cones, and you will see we define a general functional covers this functional as well. So this functional becomes just a simple case for our functionals. But in Pascoaletti-Serafini, we try to minimize t subject to this constraint, and this is, you can look at it as a minimization of a functional. So at any point, even another point here, y1, you are trying to see which point, the small, you want to find, you want to calculate a sub-optimization problem and see which one has a lower t. Because if you find that, then it's a non-dominated element. It's the minimal element as well. So you try to minimize this functional, and so Pascoaletti-Serafini approach is equivalent to minimization of a functional. And you can characterize these non-dominated elements. And here, for example, if y bar is a non-dominated element with respect to the ordering, then again, minimization of the functional helps us, because you can find those minimal solutions as well. This holds even for if y bar is a weakly non-dominated elements. Here we don't care about if it is weak or not, but here we care about weakness as well. So if it is a weakly non-dominated elements, then it is a minimal solution as well. So we can, in last lecture, lecture 7, I will show you how you can find those minimal points using just this minimization of this functional psi, minimization of psi. You can find those unique minimal solutions.